First thing you do is draw a picture of the manometer. We see that this is an open arm manometer. It is 6 millimeters higher on the gas side. So if we can imagine a picture, we would notice that the pressure of the atmosphere must be greater than the pressure of the gas. We then will have a delta H equal to 6 millimeters of mercury.
No, I am.
Because the gas pressure is less than the atmospheric pressure, we will subtract the delta H off of the atmospheric pressure. We must have the same units, and therefore we must convert 6 millimeters of mercury into kilopascals using the conversion factor of 760 millimeters of mercury equal 101.3 kilopascals. From that we get a value of 0.8 kilopascals, and then we subtract the value 0.8 from the atmospheric pressure to get the pressure of the gas, which then becomes 101.3 minus 0.8, or 100.5 kilopascals. In this problem, we see that we are dealing with a closed arm manometer. The delta H for this closed arm manometer is 238 millimeters of gas. The question asks, what is the gas pressure in atmospheres? Well, in a closed arm manometer, we know that this is actually a direct measure of the pressure of gas. Therefore, we only need to convert the units and make them consistent, or answer the question properly. The delta H is given as 238 millimeters of mercury, and the pressure for the answer needs to be in atmospheres. So we will convert using the conversion factor that 238 millimeters of mercury will be converted into atmospheres by using the conversion factor of 760 millimeters of mercury per 1.00 atmospheres. We simply cancel out the units, as we have done many times in converting one thing to another, and we obtain the value of 0.313 atmospheres. Looking at the significant figures, we see that there are 3 significant figures in the number 238. Therefore, we include 3 significant figures in the answer, 0.313. This is a problem involving Dalton's law. We have a mixture of oxygen, carbon dioxide, and nitrogen, which has a total pressure of 0.97 atmospheres. The question asks, what is the partial pressure of oxygen if the partial pressure of CO2 is 0.70 atmospheres and the partial pressure of N2 is 0.12 atmospheres? We know that the total pressure is equal to the partial pressures of each gas, which is equal to 0.97 atmospheres. We will write out the equation. we will solve for the variable pressure of oxygen, and we will substitute in the values that are given. Pay attention to units and significant figures. And this simply becomes a math problem where the pressure of oxygen, partial pressure of oxygen gas is equal to 0.15 atmospheres. This is another Dalton's law problem. You're presented with the percent composition of the atmosphere or air, and you are told that the atmospheric pressure, or in other words, the total pressure, is 760 millimeters of mercury. What are the partial pressures of N2, O2, and argon in the atmosphere? The total pressure of the atmosphere is given as 760 millimeters of mercury. Convert the percents to decimals. So we will multiply the pressure of, to get the partial pressure of nitrogen, the total pressure of the gases times the percent of the atmosphere that represents nitrogen, which is 0.78. We'll do the same thing for the pressure of O2, 760 times 0.21. And finally, the pressure of partial pressure of argon, which is 760.01. Once we've done this, laid it out the equations, now we just have to do the math. And the partial pressure of nitrogen comes out to be 592.8 millimeters of mercury. The partial pressure of oxygen comes out to be 159.6 millimeters of mercury. And the partial pressure of argon comes out to be 7.6 millimeters of argon. And that is basically that problem. The total should be around 100%. Might want to check that. In this slide, we are looking at Boyle's law. Boyle's law states that the volume of a fixed amount of gas held at constant temperature varies inversely with the pressure. In other words, as the pressure goes up, the volume goes down. Important thing to note here, that the temperature is constant and that the temperature is in Kelvin. Again, this is Boyle's law. This problem is an application of Boyle's law. A diver blows a 0.75 liter air bubble 10 meters underwater. As it rises to the surface, the pressure goes from 2.25 atmosphere to 1.03 atmosphere. What will be the volume of the air in the bubble at the surface? First, we want to organize our data by listing it on the side, being careful that we include all significant digits and label with appropriate units. It's good to have your data organized. It will make life easier later on as you do more complex problems. We are looking, therefore, for V2, the volume of the bubble under the new conditions. First, we write out Boyle's law, P1V1 equals P2V2. We will solve for V2, as that is the volume under the new pressure. So we do our algebra, and we find that V2 equals P1V1 over P2. We substitute in our data, which we have organized on the left-hand side. It is best to include units with your substitutions. I don't have the space here, so I have not included the units, but it would be a really good idea to do that. If you then check your units, that you'll find out that the units for pressure will cancel, and that your final answer will have units of liters, which is the correct unit for volume. And finally, you're going to check your units and your significant digits. In this case, we probably have one extra digit in the answer than we need, so we would round to 1.6 liters.
Free information kit and no
All right, let's see if I go back to this one.
Oh no, this one.
This is another Boyle's law problem. Very similar to the one we just did. So I would suggest you practice this on your own and check the answer on page 443, practice number 1. And go there for the answer and to get more information on how to do the problem. This is exactly like the last one. The answer for this problem is 157.98 milliliters. Looking at the significant figures, we see that 3 would be the limiting number, and therefore we round the answer to 3 significant figures, or 158 milliliters. We see that this is done at constant temperature. This is the second gas law, called Charles's law. It deals with temperature on the Kelvin scale. Absolute zero is 0 on the Kelvin scale. Charles's law states that the volume of a given amount of gas is directly proportional to its Kelvin temperature at constant pressure. Therefore, if we have the Celsius temperature, let's say it's 100, we will simply add 273 to make the Kelvin temperature equal to 373 degrees Kelvin. V1 and T1 are the initial conditions, V2 and T2 are the new conditions, and we will look for a given variable. So this is a direct relationship. The V stand for volume, and the T's for temperature. In Charles's law, we are dealing with constant pressure. This is another example of Charles's law. It can be found on page 446 and example number 2 in your textbook. We have a helium balloon in a closed car. It occupies a volume of 2.32 liters. So T1, and the temperature is 40 degrees C. We should immediately convert the temperature into Kelvin by adding 273. Because it's a hot day, the temperature inside the car rises to 275. That will be T2. And the question asks you what it will be the new volume of the balloon. That will be V2. We will set up the Charles's law. V1 over T1 equals V2 over T2. We're looking for V2, so we will solve for V2. That is equal to V1 T2 over T1. Now we sub in the data. V2 equals 2.32 liters. T2 is 348 Kelvin. T1 is 313 Kelvin. We solve for V2, which is equal to 2.58 liters. The data looks like it has 3 sig figs, so 2.5 liters is an acceptable answer. This is another Charles Law practice problem from your text, page 446. We have a balloon which has a volume of 4.3 liters and at a temperature of 350 Kelvin. The question asks, what is the new volume if the temperature is decreased to 250 Kelvin? In thinking about this, what should we expect? We should expect that the volume would go down. We will do Charles' law again. The new temperature is 250 Kelvin, which is 100 Kelvin less than the original temperature. We are looking for V2, the new volume. So we set up Charles' law as before. V1 over T1 equals V2 over T2. We will solve for V2. V2 equals V1 times T2 over T1. Substitute the data in. Try and put the data in correct. Be sure and put the data in correctly. And now we will solve for V2. The value of V2 is equal to 3.1 liters. Sig fig wise, it looks like we have 4.3, and therefore we'll have 2 sig figs in the answer. The next law is Gay-Lussac's law. This is the third gas law, and it relates pressure with temperature and assumes that the volume remains constant. It is a direct relationship, so as you increase the temperature in Kelvin again, you will be increasing the pressure, and that's assuming that the volume remains constant. So if you had a pop bottle and it had a fixed amount of gas and you increased the temperature and you could not change the volume, then the pressure inside the pop bottle would increase. In this diagram, we have an example of the Gay-Lussac's law, where we have a fixed volume of 1 liter, and the temperature, which starts at 150, is increased to 300 K. And so as the temperature increases, the pressure on the tank will double. So as we go from 1 atmosphere pressure at 150 K, the pressure doubles to 2 atmosphere at 300 Kelvin. And the reason that is the temperature rises, is that the number and the force of the collisions of the gas particles on the sides of the wall of the tank are going to double. And recall that the pressure on the inside of the wall, the pressure inside a tank, is due to the number and force of the collisions within the walls of that tank. Again, we're holding volume constant in this case. This is an example, an application of the GL law. It is on page 448 of your textbook. We have a container of oxygen at a campsite on Mount Everest. The initial temperature is 25 degrees C, and the initial pressure is 5 atmospheres. If the temperature there falls to 10 degrees C, what is the new pressure inside the container? We want to organize our data on the left-hand side. T1 is set at 25 degrees C, which we convert immediately to Kelvin by adding 273. The initial pressure, or P1, is 5 atmospheres. The new temperature will be dropping to 10 degrees C plus 273, which equals the new temperature is actually minus 10 degrees C, and therefore the T2 is 263. We're solving for P2. P1 over T1 equals P2 over T2. We're looking for P2, the new pressure. So we solve for P2. We substitute the data into the equation. We need to be sure that we include the 3 sig figs. The answer comes out to be 4.41 atmospheres. This is another example of the GL law. It is on page 448 of your textbook, practice problem number 8. Let's put our data on the left-hand side. P1 equals 1.88 atmospheres. At an initial temperature, or T1, equals to 25 degrees C, which we will convert to Kelvin. That gives us 298 Kelvin. The new temperature increases to 37 degrees C, which again we will P2 is the new pressure that we're looking for. As we have increased the temperature, we would expect that the pressure will probably have to go up since the volume must remain constant. So I'm going to write out the GL law, P1 over T1 equals P2 over T2. We are looking for the new pressure, P2, which equals P1 T2 over T1. We will substitute the data in. Try to be sure and use your units. I run out of room, so I can't use them here. But the units will help you be sure that you're solving the right thing and doing the right math. So we get P2 equals to 1.9557 atmospheres, but we see that we have 3 sig figs, and so we should round it to 3 sig figs, which will give us an answer of 1.96 atmospheres. This is the combined gas law. This is the most useful of all the gas laws that we have seen thus far, because it combines the first three in one nice equation. You will want to memorize this equation or put it on your equation sheet, but it does combine the relationships between pressure, temperature, and volume for a fixed amount of gas. And we can use this equation to derive the other three. The T is temperature, of course, in Kelvin. We have pressure, P1 or P2, in units for pressure of atmospheres, kilopascals, or millimeters of mercury. Volume is in liters, or it could be in milliliters as well. And so these are all the same variables we've seen in the Boyle's, Charles, and GL law, but now we have them all in one. Now this is our first use of the combined gas law to solve a problem. You will find this on page 450 in your textbook. We have a gas at 110 kilopascals and 30 degrees C. It fills a flexible container with an initial volume of 2 liters. If the temperature is raised to 80 degrees C and the pressure increases to 440 kilopascals, what is the new volume? We need to organize our data on the left-hand side. P1 is equal to 110 kilopascals. T1 is equal to 30.0 degrees C, which we will convert immediately to Kelvin. That's equal to 303. V1 is 2 liters. P2 is raised to 440 kilopascals. And we are looking for the new volume, or V2. T2 is raised to 80 degrees C, which we convert to Kelvin. And we are looking at V2. So we're looking for V2. We'll write the combined gas law. P1 V1 over T1 equals P2 V2 over T2. we're going to be solving for V2. Just solve, and now we're going to substitute the values in. The best thing you can do, if you can, is to include all the units with your data. I can't always fit it all in. This time I can. So we have 303 Kelvin, 440 kPa, kilopascals, and V2 is now equal to 0.58 liters. It looks as though we could actually have 3 significant figures in this answer, so while I carried it out to 2, you may need to add a third. And that's it for this combined gas law problem. This is another combined gas law problem, page 450, number 12 in your text. A balloon contains 146 milliliters of a gas confined at a pressure of 1.30 atmospheres and a temperature of 5 degrees C. If the pressure doubles and the temperature decreases to 2 degrees C, what will be the volume of the gas in the balloon? Again, collect the data on the side. V1 equals 146.0 milliliters. If we're looking for the new volume, so the units aren't specified, so we'll go with milliliters. We have P1 equal 1.30 atmospheres. T1 is equal to 5 degrees C. Convert to 273. Convert to Kelvin by adding 273. T2 is now 2 degrees C, and the pressure is doubled at 2.60 atmospheres. What is V2, the new volume? So we write out the combined gas law. I'm just going back and converting the temperatures into Kelvin. Forgot to do that in the beginning. We write out the combined gas law. P1 V1 over T1 equals P2 V2 over T2, and we will solve for V2. So we solve for V2 equals P1 V1 over times T2 over T1 P2. Substitute all the data in. Try to substitute in with all the units. so that you can do a unit check. V2 then equals 72.2 milliliters. And since the problem doesn't specify what the volume needs to be in, what units, then you can leave the volume in milliliters. Do your quick unit check, and that will show you that you should get milliliters for your answer, and that is what we get. And that's it. That's another combined gas law problem. This slide is an illustration of Avogadro's principle. Avogadro's principle states that equal volumes of gases at the same temperature and pressure contain equal numbers of gas particles. And this goes back to the idea that 1 mole of gas at STP conditions is equal to 6.02 times 10 to the 23rd gas particles, regardless of the gas involved. And this simply shows the fact that CO2 and carbon dioxide, or CO2, which is nonpolar, helium, and oxygen, which is O2, those samples, if they're at the same pressure, will contain the equal number of gas particles. Pressure is like concentration for a solution. So the higher the pressure, the higher the concentration of the gas. That's one way of thinking about it. This is a very important idea to keep in mind. In this slide, we explore the idea again of a molar volume, which was introduced to us from the stoichiometry unit in dealing with gases. And again, at STP conditions, which is 0 degrees C for temperature and 1 atmosphere pressure, 1 mole of gas will occupy 22.4 liters. Now that we're talking about gases, we have different conversion factors for the units of pressure. We have 1 atmosphere is equal to 101.3 kilopascals, which is equal to 760 millimeters of mercury, which is equal to 760 torr, or 29.92 inches of mercury. So we have a variety of units for pressure now that we're talking about gases. This is called the kinetic molecular theory for gases. It's made of a number of assumptions, one of which is that gases consist of very small particles and therefore essentially have no volume. It's not saying that they have no mass, it is saying that they have no volume compared to the volume of the container that they're confined in. The KMT theory, as it's called, also assumes that these gas particles are so far apart and moving so fast that they do not interact with each other. In other words, there's no IMFs. And recall, IMFs from a previous unit includes things like dispersion forces, hydrogen bonding, and dipole-dipole forces. So the assumption is that gas particles have no interaction whatsoever in this KMT theory. We'll see later that some gases are more in line with that assumption and others are not. More ideas on the KMT theory include that gas particles are in constant random motion. This is due to their kinetic energy, and as we know that as you increase the temperature, the kinetic energy also increases. Another assumption under KMT theory is that all of the collisions are elastic, which means that when they collide with one another or the sides of the container, that no energy is lost. So again, that is an assumption that's not necessarily true, but it does work in KMT theory. This is, again, the kinetic molecular theory model. And another idea in this model is that the kinetic energy of a particle depends on the mass and its velocity. In other words, Ke, kinetic energy, is equal to 1/2 mv squared, which is an idea you've seen before in your physics or your CPS class. Temperature is a direct measure of the average kinetic energy of the particles in a sample of matter. So the higher the temperature, the higher kinetic energy of the particles. That does not mean that all molecules of gas at the same temperature will have the same velocity. But it does mean that gases at the same temperature have the same kinetic energy. And that's an important distinction, that the larger the gas molecule, the slower it's going to move. So CO2 moves more slowly than helium, even when their kinetic energies are the same. All right, so that's some more information on gases. This brings us to a very important law, probably more useful even than the combined gas law, and that's called the ideal gas law, otherwise known as PV equals nRT. Around here, it's called PIV-NERT. That's an affectionate term known only at McQ. The pressure is represented by P. V is volume. N is the number of moles of the gas. R is something called the universal gas constant, or the ideal gas constant, and T is the temperature in Kelvin. This is a law that we will be using a lot, and if you look at it, the new variable N is introduced, and that represents a given amount of gas. We have another variable called R, the universal gas constant, and R will depend on the unit of pressure that's being used for P. There will be a range of R's provided, and you have to choose the R value which corresponds to the same units you have in your pressure value. This is the values for R, the ideal gas constant, often called the universal gas constant, and it's used in the ideal gas law. The value of R, as I mentioned, depends on what the units are for pressure in your exact calculation. If the unit of R of pressure is in atmospheres, then you pick the first R, the value of R of 0.0821 liter atmosphere per mole Kelvin. If your pressure has units of kilopascals, then you pick the second value of R of 8.314 liters kilopascals per mole Kelvin. Finally, if your units for R units of pressure are in millimeters of mercury, you would select a value of R equal to 62.4 liter millimeters of mercury per mole Kelvin. So you see, it's very important to know what units your pressure value is in, so that you may select the correct value of R when using the ideal gas law. Now let's practice the ideal gas law. This is practice problem number 6 on page 455 of your textbook. It says to calculate the number of moles of ammonia gas, NH3, contained in a 3.0 liter vessel at 3.00 times 10 to the 2 Kelvin with a pressure of 1.50 atmospheres. Let's collect the data on the left-hand side. N is the number of moles, and that's what we're looking for. V is the volume at 3.0 liters. T equals 3.00 times 10 to the 2 Kelvin, and the pressure given is a 1.50 atmospheres. So now we're going to write out, excuse me, the ideal gas law. PV equals nRT, and we are solving for N, the number of moles of gas. So N will become PV over RT. Now substituting the data into the equation, we have 1.50 atmospheres. We have a volume of 3.0 liters. We must select the value of R consistent with the units of pressure. Referring back to the previous slide, that would be a value of 0.0821 liter atmosphere per mole Kelvin times the temperature in Kelvin. The temperature was given in Kelvin, so we didn't need to convert it. N, R again needs to have units of atmosphere. And that will be given to you on a chart during an exam. Once we choose the correct R, check our units, we find out everything cancels except for moles. Moles is what we're looking for, so that means we have set the problem up correctly. Now we simply solve for the value of N. That comes out to be 0.183 moles of ammonia gas. Looking at the significant figures, we could round this to 2 since the volume is only given to 2 significant figures. And we would round this then to N equals 0.18 moles of ammonia. All right, so that's another example of the ideal gas law. We'll take a look at some others. This is another application of the ideal gas law. It is number 26 on page 455 of your textbook. The question asked you to determine the Celsius temperature of 2.49 moles of a gas contained in a 1.00 liter vessel at a pressure of 143 kilopascals. So again, organizing our data, we are looking for the temperature, that's our unknown. N, the number of moles of gas, equal 2.49. The volume is a 1.00 liter vessel, and the pressure is 143 kilopascals. In choosing an R value for this, we will be looking at the units of pressure, which are kilopascals. And going back to the chart, we will find that the value of R that must be used corresponds to 8.314 liter kilopascals per mole Kelvin. Now we write the ideal gas law equation. We're solving for T in Kelvin. We write the ideal gas law equation, PV equals nRT. We solve for T. T is equal to PV over nR. We then substitute the data into the equation, 143 kilopascals, 1.00 liters, divided by 2.49 moles, and the 8.314 liter kilopascal mole Kelvin for the units. T then is equal to minus 273, which when converted back into Celsius is equal to minus 266.09 degrees Celsius. You could have done a unit check there as well. I didn't show it in the problem, but it would be a good idea just to check all your units. You find out you get have units of Kelvin left. When you find the temperature, you then want to go back and convert it to degrees C. And that's another application of the ideal gas law. This is some extra practice using the ideal gas law. The question asks, what volume will 20 grams of argon occupy at STP? Again, we'll have to go back. Standard temperature and pressure. Standard temperature is 273 Kelvin. Standard pressure is 1 atmosphere. And we have 20 grams of argon. And we're looking for volume. So we're looking for volume. We also have not been given the value of N, the number of moles, but we can figure that out. We can convert the number of moles we can take the 20 grams of argon and convert to moles using its molar mass. So if you look on the periodic table, argon has a molar mass of 40 grams per mole. And that will, if you look at the unit check, that gives you moles of argon. It does tell us that we are at STP, so thinking back to the days of stoichiometry, we can use the relationship that 1 mole of any gas has a volume of 22.4 liters at STP, and that would give us a value of 11.2 liters of argon gas at STP. Another way to have done this would be to have calculated the value of N, the number of moles, substituted into PV equals nRT, and solve for V. Obviously, the shortcut here is an easier way of going about it, but you can also utilize the ideal gas law for solving this problem as well. In the second problem, they are asking how many moles of gas are contained in 890.0 milliliters at 21 C and 750 millimeters of mercury pressure. So the volume is equal to 890.0 0.0 milliliters. The temperature is 21 degrees C, and the pressure is equal to 750.0 millimeters of mercury. In order to use PV equals nRT, and we are looking for N, so N equals PV over RT, we must first convert the 890.0 milliliters to liters. That can be done relatively simply. And we have a matter of the pressure, 750 millimeters of mercury. That's a little less common, but we do have an R value for that. So we'll use it as millimeters of mercury. Um, 750 millimeters of mercury. The volume we had to convert to liters, must be in liters, 0.8. So divide by 1,000, 0.8900 liters. Picking the right R, the R value a few slides back, I believe, was 62.4 millimeters of mercury per liter per I have to check on these units. Let's see, millimeters of mercury per mole Kelvin. 62.4 millimeters of mercury liters mole Kelvin, and then the temperature has to be converted into Kelvin, so 21 plus 273 Kelvin. So there's really no more space here to do the work. The answer does come out to 0.036 moles. So in this problem, there were a number of conversions that had to be done. Do check your units before going through and doing the math. The answer then in the end is 0.036 moles. This is another practice problem for the ideal gas law. You can find it on page 455 of your text. It says calculate the volume. So we're looking for a volume of a 0.323 mole sample of a gas. So N equals 0.323 moles. And the temperature is 265 Kelvin. And the pressure is 0.900 atmospheres. And we will need to find the correct value of R, the universal gas constant. We start with PV equals nRT. We are looking for the volume, so V equals nRT over P. And if we substitute everything in, we have 0.323 moles. We'll use the 0.0821 liter atmosphere mole Kelvin. For R, we have 265 Kelvin all over a pressure of 0.900 atmospheres. Doing the math, we end up with a value of 7.808 liters. Looking at the number of significant digits, it would seem like 3 is a reasonable number. So we will round this to 7.81 liters. And again, this is just using the ideal gas law. The main thing is converting volume to liters, temperature to Kelvin, and finding the correct value for R, the universal gas constant. This problem is actually a question about using the combined gas law to determine the volume of a gas at new conditions. So again, I would use the combined gas law for this problem rather than the ideal gas law. We have the same sample of gas, the same amount of gas, and the only thing that's changing is the conditions under which the gas is being held. So you would start with the combined gas law, which would be P1V1 over T1 equals P2V2 over T2. And again, knowing the STP, so those are, we have a V1 equals of 10.0 mils, T1 equals 60.0 degrees C plus 273. First pressure is at 75.6 kilopascals. And the volume, the new volume is V2. The new pressure and the new, nope, V2 is what we're looking for. The new pressure will be 1 atmospheres, or P1 is in kilopascals, so 101.3 kilopascals. The T2, standard temperature, is equal to 273 Kelvin. So now you're subsolving for V2. V2 equals T2 P1 V1 P2 T1. Substitute it all in, and you get an answer of 6.118 milliliters. Looking back at the data, you may want to round to 3 sig figs, so 6.12 milliliters. And there again, that's really a combined gas law problem rather than an ideal gas law problem. Your sample is staying the same, and you're just changing the conditions under which the gas exists. Okay, this is another example of the ideal gas law. We have a steel tank. It has a volume of 438 liters. It is filled with 0.885 kilograms of O2 gas. We are looking for the pressure of the O2 gas, and the temperature is 21 degrees C. Add 273 to convert it to Kelvin. That comes out to be 294 Kelvin. Again, we want to do PV equals nRT. We're calculating P in this case, so we solve for P equals nRT over V. We then substitute it in. We need a value of N, which turns out to be the number of moles of oxygen gas. So we need to do some conversions first. We will go up here, 0.885 kilograms of O2. We need to convert back to grams. So 1 kilogram is 1,000 grams. And that gives us 885 grams of O2. Now we must take 885 grams of O2 and convert to moles. So we know O2 is a diatomic, 32.00 grams per mole of O2 gas. That gives us a value of 27.66 moles of O2. And now we've actually run out of room, but you need to substitute everything in. Pick the R, our pressure. We can pick any R because the pressure is being calculated. And so substituting everything in, the value of P comes out to be 1.52 atmospheres. So I ran out of room there, but in terms of calculating P, you simply need to put in the values for N. Choose R. We're looking for atmosphere, so we'll use 0.0821. Temperature was in Kelvin, 294 Kelvin, and divided by the volume, which was already in liters, so 438 liters. Check your units, do the math, you come out with an answer of 1.52 atmospheres. This is actually a combined gas law problem, where I'm not going to go through it. You can do it on your own. Combined gas law. And will the safety valve open? The pressure at 100 degrees C will come out to be 1.25 atmospheres. And the pressure at which the valve blows or opens is equal to 1.316 atmospheres. And if you follow through with the problem, then the valve will not open. So you can work this one through on your own. It's a little bit more involved than we would probably have on a problem.